Hey everyone! Today we're going to be taking a further look at periodic trends, but this time we want to focus a little bit more on how to write out a thorough explanation for why the trends are what they are. To help us with our explanations, we're going to be using a format that's called CER. That stands for Claim, Evidence, Reasoning. This is similar to the CDC's Claim Data Commentary that you may have used in other classes such as English or history. In science, we typically call it Claim, Evidence, and Reasoning. And it's going to help us support our answers in a way that shows we understand how periodic trends work and why they work the way they do. So what we're going to do is work a few examples kind of using the CER format. It will help us review our trends while at the same time practicing some good evidence-based writing. Now we're going to structure our CER responses as follows. Our claim is just going to be a simple answer to the question that we are asked about the periodic trend. Our evidence section will have us looking at the periodic table to cite some specific evidence about atomic structure. Then finally, our reasoning is going to have us connect that evidence to the periodic trend in question. And so let's kind of walk through a few examples together. So it's going to start out with a question such as, which element has the smallest atomic radius? Si, silicon, or Cl, chlorine. Justify your answer using CER. So in the claim, that's simply where you're going to state a very direct and concise answer to the question. So we were asked, which element has the smallest atomic radius? If we look those up on our periodic table, let's kind of split our screen here so we can view this. And you'll want to have your periodic table handy. So if we find chlorine and silicon, those are our two elements here, we know that in general, as you go further right, the elements get smaller. So that's how we were able to generate our claim or our answer to the question. So that's what you start off with, just answer the question that you're asked. Now is where we need to get specific for our evidence section. Now, the evidence that we list is going to be dependent upon whether the elements in question are a part of the same row, aka a period, or a part of the same column, aka a group. Now, if you think back to the lesson that you had with your teacher on periodic trends, you would have remembered that as you go across a period or a row, what happens to the atomic structure is that you're gradually gaining more protons. However, when you're in a group or a column, as you go down that group, you're steadily gaining more energy levels or shells. So if you're in a period, the evidence is going to be related to protons. And I remember that by looking at the P's. P for period, P for protons. If you're in a group or a column, you're going to be looking at the number of energy levels or shells. G for group, and G for energy levels. So if we look at our two elements in question, chlorine and silicon, they're going to be in the same row or the same period. So our evidence needs to be based on their number of protons. Now again, we want to be specific and tell how many protons each of those atoms has. If you'll remember, the number of protons is found at the top of the periodic table square. It's the same thing as the atomic number. So we see that silicon has 14 protons and chlorine will have 17. So that is our specific evidence that relates to those elements being in the same period as each other. Now, after our evidence, it's time to go on to the reasoning section, which is where we connect the evidence to the claim that we wrote. Now, I have 3 bullets here to kind of help us think about what we need to include as a part of our reasoning. And as you get more experience, you'll kind of get a feel for what to include, but initially this will help us track our responses. So the first thing we're going to do is summarize our evidence with just a general statement. So you'll notice in the evidence section we got pretty specific. But here's the way we can summarize that. So instead of saying chlorine has 17 protons, silicon has 14 protons, the way we can summarize that is saying that chlorine has a greater number of protons than silicon. So that's just a general restating of our evidence. And the second part of our reasoning is we need to somehow talk about how that evidence is connected to the effective nuclear charge. And so that's what ZEF stands for again, is effective nuclear charge. And essentially that is just equal to the attractive force between the outer electrons and those protons that are inside in the nucleus. So if something has more protons, it's going to have a greater or a stronger effective nuclear charge. So there's our connection to the attractive force. Then finally, one of the things that's very important not to leave out of your reasoning is to connect this back to the definition of whatever trend is in question. For example, in this case, we've been asked about atomic radius, which means that we need to connect our question back to what atomic radius means. We know that radius is referencing size. So here's how we tie that in. So if we start from the top, it says chlorine has a greater number of protons than silicon. Chlorine will have a greater effective nuclear charge, and here's the connection. So its electrons will be more tightly attracted to the nucleus, resulting in a smaller size or radius. So we connected that greater attractive force with the electrons becoming more tightly held, and that's going to create a smaller size. All right, so now let's try another one of those, kind of following that same pattern. So this time we're posed with two different elements, and again we're asked which one has the smallest atomic radius, potassium or cesium. So what let's do is let's look on our periodic table, find our elements, and go ahead and generate an answer to our question, aka a claim. So potassium and cesium are on this left side of the periodic table. Let's move it over where we can see. Here they are. All right, so here's potassium and here is cesium. So we know that atoms get bigger as you go down the group, so that must mean that potassium is smaller. So our claim is just simply to answer that. Potassium has a smaller atomic radius than cesium. Nice, short, and simple. Now we need to get specific and list our evidence. In this case, these two elements are in the same group or column. So G group means we need to be specific about the number of energy levels or shells. Now on your periodic table, depending on which copy you have, you're going to have numbers for the different periods. The numbers represent how many energy levels you have. So for example, potassium is in this fourth row, so it's going to have its valence electrons on the fourth energy level. Cesium is in the sixth row, so it's going to have its electrons on the sixth energy level. So here's our evidence. Potassium has its valence electrons, spell electrons correctly, on the fourth energy level. Cesium has its valence electrons on the sixth energy level. All right, so now we've got our specific evidence and we want to be able to put that in our reasoning. So the first part of our reasoning is just to summarize our evidence with a general statement. So in general, potassium has fewer energy levels than cesium. And I'll keep the symbols just to be consistent. So potassium has fewer energy levels than cesium. With fewer energy levels, you're going to have a stronger attractive force, and you're also going to be a smaller atom just because you have less layers or less shells. A lesser number of energy levels results in a smaller atom overall. And so that's what leads to that smaller size or smaller radius. And you'll notice here we didn't really have to get into attractive force as much, because when you're talking about size, if it's just based on energy levels, well, the more energy levels you have just naturally implies that your atom is going to be bigger. And so that doesn't quite as much depend on the effective nuclear charge as much as the other trends will. So that's kind of the only one where you don't have to make quite that direct connection. But let's keep practicing with 2 more examples and we'll see how that ties in all the rest of the times. Okie-doke. So here we have a question about ionization energy. Now when you come to a question about a trend, it's important that you first take some time to remember, well, what does that trend actually mean? So let's take some time and just redefine what ionization energy means. So what that is it's the energy required to remove an electron from a neutral atom. And so what that means, if the electron is harder to remove, it's harder to remove the electrons, that's going to be equal to a higher ionization energy. If it's easier to remove the electrons, that's going to be equal to a lower ionization energy. So that's the way this trend happens to work. All right. So again, which element has the lowest ionization energy, Br or I? Justify your answer using CER. So first, let's find them on our periodic table, and we'll just make a general claim that answers the question. Here we have bromine and iodine. As you go down the periodic table, the atoms have a lesser attraction for their electrons. They're bigger, their electrons are farther away, and so the ionization energy decreases as you go down. So this results in iodine having a lower ionization energy than bromine. These elements are in the same group, which means that for our evidence, G group requires that we get specific about energy levels. So if we look at our numbering out to the side of our periodic table, we see that bromine is in the 4th row and iodine is in the 5th row. So we'll be specific and say that iodine has its valence electrons on the 5th energy level and bromine has its valence electrons on the 4th energy level. So now we're ready to connect that to our reasoning. So in our reasoning, let's split our screen so we can see our outline here. So with our reasoning, we want to start by generally summarizing our evidence. So our evidence said that in general, the valence electrons of iodine are on a higher energy level than the valence electrons of bromine. Now, we need to connect this greater distance to a stronger or weaker attractive force. So if the electrons are farther away, what that does is causes them to experience a weaker effective nuclear charge. So there's our connection to the attractive force. Then finally, we want to connect it back to our definition of the trend, which is what we talked about earlier, that ionization energy is the energy needed to take away an electron from a neutral atom. So it says since iodine's electrons are farther away, they experience a weaker Zeph. And then here's the connection. This makes its electrons easier to remove, resulting in a lower ionization energy. So a great solid reasoning that connects our evidence to our answer. All right, so here's the number 4 CER example for us to try. So again, we're still working with ionization energy, but this time we've got sulfur and chlorine. So let's find those on our periodic table. And here they're going to be asking us to choose which one has the largest or highest ionization energy. So if we circle sulfur and chlorine, those both happen to be in the same period or row. We know that as atoms get across, they become stronger and it's more difficult to remove their electrons. So chlorine will have a higher ionization energy than sulfur. So that's our claim. Chlorine has a higher ionization energy than sulfur. We're in a p period, so our evidence needs to be p protons. So let's list our specific protons. Sulfur has an atomic number of 16, so it will have 16 protons. And chlorine will have 17 protons. Finally, let's tie everything together with our reasoning. We'll begin by summarizing the evidence with a general statement. So in general, we see that chlorine has more protons than sulfur. All right. So now that we've got our general summary, we're ready to show how this evidence affects the effective nuclear charge. If it has more protons, it's going to make the effective nuclear charge greater. This will make chlorine's effective nuclear charge greater, or you can say the word stronger, either way. Now, last but not least, we need to tie this back in to the definition of the trend that's at hand. In this case, we're going to be talking about ionization energy. So let's get our highlighting to color code. Now we need to connect this back to energy. So if chlorine has a stronger effective nuclear charge, its electrons will be more tightly attracted and will be harder to remove. This makes the ionization energy higher. So again, we're showing that we understand what ionization energy means and how it relates to differing numbers of protons. And you'll notice when we frame our reasoning, we frame it to kind of line up with our claim. In this case, they're asking which element has the largest ionization energy. And so, since chlorine did have the largest ionization energy, we're going to frame our answer based around chlorine. If they had reversed the question and said which element has the smallest ionization energy, that would be sulfur, and we would instead base our reasoning off of sulfur. For example, we would have said sulfur has less protons than chlorine. This will make sulfur's effective nuclear charge weaker. Its electrons will be less tightly attracted and easier to remove, making the ionization energy lower. So it just depends on whatever the answer to the question is. All right. So Chem 1, if you are with us, you will be actually stopping the video now and going ahead and completing the practice slides that will work you through some more CER practice problems. If you're pre-AP, hang with us just a little bit longer. We have 2 additional learning targets to cover that have to do with ions and also isoelectronic atoms. And so I'm going to give us just a little more space here. That way we can fit our whole chart on. We'll finish this up and then we'll get you guys going for your practice as well. So thanks so much, Chem 1. We'll see you. Pre-AP, hang tight. Let us finish this last part first. All right. So pre-AP, here we are. So what we're going to be covering is 2 additional learning targets that are important kind of within this section of periodic trends. And so the first one has to do with comparing the radii of cations and anions versus their parents. And so when you have a cation, what happens is that is an atom that has lost electrons. And so overall, that atom is going to be positively charged. Now, if we look at this little diagram here, the parent atoms are going to be the atoms that are neutral. So for example, you might have a parent atom of potassium, which is K, and the cation might be K+, indicating that 1 electron has been lost. So if we compare these 2 atoms here, let's pretend this is K and this is K+, what we notice is the cation is smaller than the parent. It kind of fits inside of it. So what we see is that the cation is smaller than the parent atom. Now, if we look at the anions, on the other hand, that is an atom that has gained electrons, and so will have an overall negative charge. So that might be an example of bromine as the parent atom and Br minus as the anion. It's gained one extra electron. If we compare these, we see that the anion form is larger than its parent atom. So what we might type here is that the anion is larger than the parent atom. And so what we're going to do is see if we can kind of look at an explanation for why ions differ in sizes from their parents. So let's tackle cations first. So here we've got kind of Ca versus Ca2+. And so if we look at these, they're both calcium. And so what that means is that their number of protons is going to stay consistent. I'm going to give myself a little more room here. And so if we find calcium on our periodic table, we'll pull it up one more time. Calcium is going to have 20 protons based on its atomic number. Now, what is going to change when you have an ion are the electrons. For the parent atom, it's neutral, so the protons will be equal to the electrons. For the ion, the positive charge indicates that some electrons have been lost. In this case, the positive charge 2+ indicates that 2 electrons are missing. So instead of 20 electrons, you only have 18. And so this reasoning is going to be based on the relative differences between the numbers of electrons per the numbers of protons. And so what we see that happens with this cation is that you have less electrons per the same number of protons. And so I've got it written out here above for the explanation. So what happens is that the loss of electrons means that there's an increase in the effective nuclear charge because the number of protons, which remains unchanged, are attracting fewer electrons. So they have less electrons to have to hold together. So what that does is whatever electrons are left are going to be attracted in more closely and more tightly held, which will result in a much smaller atom. So that increase in effective nuclear charge due to having less electrons, those remaining electrons will be pulled in more closely, more tightly held, and as a result, you're going to end up with a smaller radius for your atom. Now, if we examine this trend in anions, the opposite effect will be true. Here we have fluorine and fluorine with a -1 charge. Now again, the number of protons is going to be unchanged because these are both fluorine atoms. So fluorine, if we look at our periodic table, has an atomic number of 9. So that means 9 protons will be present in each. Now, in a neutral atom, like the parent, the protons and electrons will be the same. However, in fluorine with a minus charge, that means 1 extra electron has been added. So it now has 10 electrons. That's 1 more than the number of protons. So here we see that the anion has more electrons per the same number of protons. And here's how this affects the size, as you might have guessed. So that additional electron lessens the effective nuclear charge, and that should be an E there, sorry for the typo. The additional electron lessens the effective nuclear charge as the ratio of electrons to protons increases. It's also going to create some additional electron-electron repulsion. And so that doesn't allow the nucleus to attract or pull the electrons as closely, which makes the anion larger than its parent atom. And so that just kind of shows you how to think through comparing the parent with either a cation or an anion. Now for our last learning target, we're now going to be comparing what are called isoelectronic atoms. So what ions, that's what we just did, and those are atoms with the same number of protons, but different numbers of electrons. When we're talking about isoelectronic atoms, these are going to be atoms that have different numbers of protons. They're going to be different atoms, but they're going to have the same numbers of electrons. And so that's what that word iso means, is same. So isoelectronic, same number of electrons. Now, the idea is with these trends, if the atoms have the same number of electrons, then the explanations for the trends must be based on the number of protons. And so the way it works is that, as we know, more protons is going to result in a stronger or greater effective nuclear charge. Now let's make sure first that we can identify when you have pairs of isoelectronic atoms. And so we'll get out our periodic table one more time here and show you how to know when you have a pair of isoelectronic atoms. All right, let's pull this on a blank page. That way it's just a little neater. Ah, there we go. Okay. So what you want to look for, and let's start with this calcium 2+, potassium plus here. Zoom in there. So we're going to start by finding those elements on our periodic table. So here's potassium and here's calcium. Sorry for the scrolling, it's being difficult. All right, so here's potassium, which is K. Now when it has lost one electron, that means it started out at 19, but when it loses that 19th electron, that kind of places it as if it has the same number of electrons as argon, which has 18. Now if we look at calcium 2+, that means that calcium started at 20 electrons, but it'll lose the 20th electron, lose the 19th electron, which also places it at 18 electrons, just like argon would have. So these are indeed isoelectronic atoms. Let's also look at bromine with a -1 and krypton. When you see the -1 charge, that means that an electron is added. So instead of 35 electrons, this Br- will have 36. That's the same as a neutral atom of krypton, which already has 36 electrons. So these again are isoelectronic as well. Now let's look at this top one, P3- and Br-. So if we look at phosphorus, the 3- means it adds 3 more electrons. So 1, 2, 3 to get to 18. Br- means you just add 1 more electron to get to 36. 18 does not equal 36, so those are not isoelectronic. So that's just kind of how you can tell if they fall into this category. So different atoms, but same numbers of electrons. So let's go down and answer our last example here. Whoops. Let's see if I move my words in the right spot. There we go. All right, so again, if the number of electrons is the same, we have to reason through the trend based on differing numbers of protons. So let's make a little chart just like we did before and kind of try to classify the number of protons and electrons that each of these atoms would have. If we look on our periodic table, calcium has an atomic number of 20, which means that it has 20 protons. Now, if it's 2+, that means that it has lost 2 electrons. So instead of 20, it will have gone down to 18. If I go and look at potassium, pull that up on our periodic table, potassium has an atomic number of 19. So it initially starts off with 19 protons. It has lost one of them, so it will have 18 electrons. Now chlorine has an atomic number of 17. If it loses an electron, or excuse me, this time it's actually gaining an electron because of the negative charge. So that extra electron will put it at 18. So we notice that the electrons stayed the same, but the protons are different. So what we're looking for is whoever has the most protons per the same number of electrons. So in this case, calcium has the most protons, which is going to lead to the stronger effective nuclear charge. Chlorine has the least number of protons in this case, which is going to lead to the weaker effective nuclear charge. So if we were to be asked about some trends, the largest radius would go to the weaker atom, such as chlorine. It's going to be weaker, less able to hold in those electrons. The highest ionization energy would go to the strongest atom, which is our calcium 2+. It's going to be more difficult to remove its electrons. Same for electron affinity. Calcium, having more protons, stronger effective nuclear charge, will be better at gaining or attracting new electrons. And so we can use those differences or observations about atomic structure to justify trends. All right, and so same for highest electronegativity. Is calcium as well most attractive? So thank you again, Pre-AP, for hanging in there with us. You are now ready to go and try the practice slides as well to help you just keep getting a good grip on these explanations. And anyways, thank you for your time. Good luck as you practice.